Hello everyone, welcome to my submission for assignment 2 of the CS7GV3 real-time rendering course. My name is Inkem, and in this video I'll be demonstrating and explaining the reflection and refraction effects I implemented using OpenGL and GLSL shaders. The scene contains 6 different models, all rendered using the same transmittance shader. Using different models allows us to observe how reflection and refraction behave across different shapes and surface curvature. Surrounding the scene is a skybox, which represents the environment. And at the top of the screen is a control panel that allows us to interactively adjust parameters for each individual model, as well as change the environment. Using this drop-down, we can edit parameters for each model independently. Here at the ball model, we can see effects as we move the controls. These controls include values related to reflection strength, refraction indices, chromatic dispersion, and Fresnel blending. This makes it easy to experiment with the effects in real time and compare how the same shader behaves across different geometry. Let's start with reflection. To achieve this effect, the fragment shader computes the reflection vector and samples the environment cube map to get the reflected color. Because the reflection is sampled directly from the skybox, the object visually reflects its surroundings, giving it a realistic, mirror-like appearance. And as the camera rotates, we can see the reflected environment change. Next, we have refraction, which simulates light passing through the object. Instead of using a single refraction vector, the shader computes 3 separate refraction vectors, one for the red, green, and blue color channels. Each channel uses a slightly different refractive index. These refracted directions are then used to sample the environment's cube map, creating the appearance of background distortion through the objects. Different refractive index values produce notably different visual effects. A refractive index of 1 results in little to no refraction, making the object appear almost invisible. As the refractive index increases, the bending of lights becomes stronger, leading to more pronounced distortion and a denser, glass-like appearance. This is what gives the material its transparent, transmissive quality. Another phenomenon demonstrated here is chromatic dispersion. Chromatic dispersion occurs when different wavelengths of light bend at slightly different angles, as seen in prisms or real glass. To simulate this, the shader uses different refractive indices for each color channel. This results in subtle color separation near object edges, where red, green, and blue refract differently. We can see the difference clearly in the skull model compared to the glass ball. This is because the effect becomes most noticeable at sharp edges and silhouettes, adding an extra layer of visual realism. The final appearance of the object is controlled using the Fresnel effect. The Fresnel effect describes how surfaces reflect more light at glancing angles and transmits more light when viewed head-on. The shader uses Schlick's approximation to compute a Fresnel factor based on the view angle. This factor is then used to blend between reflection and refraction. Here we can see, as we move the slider, how reflection and refraction are smoothly mixed together depending on the viewing angle. Now, if we scroll down, we see a smooth egg-shaped model and a star-shaped one with more edges. By comparing them, we can sample how geometry affects transmittance effects. Sharper edges and highly curved surfaces produce stronger visual differences, highlighting the importance of accurate surface normals in reflection and refraction. Thank you for watching.